The idea of a 90-second moment starts with something very simple, almost deceptively simple. Your body reacts quickly, and then, if nothing else interferes, it settles just as quickly. Let's take this apart carefully. At any given moment, your body is not just sitting there quietly. It's a dynamic system, full of electrical activity and chemical motion. Neurons are firing, ions are moving across membranes, molecules are binding and unbinding. It's more like a busy city than a still object. Now introduce a trigger. It could be something external, a loud noise, a sudden movement, a facial expression from someone across the room. Or it could be internal, a memory, a thought, even a vague sense that something isn't right. The moment that trigger is detected, your brain begins processing it almost instantly. Signals travel through networks of neurons, moving as electrical impulses. These signals reach areas involved in evaluation, very fast, often before you are consciously aware of what's happening. Then comes the chemical part. Your brain communicates with the rest of your body using chemical messengers, neurotransmitters and hormones. These are released into synapses and into the bloodstream. Unlike electrical signals, which are nearly instantaneous, chemicals take time to spread. But once they do, they have powerful, wide-ranging effects. Your heart rate changes. Your breathing adjusts. Blood flow is redirected. Muscles become more or less tense. Your attention narrows or sharpens. All of this is coordinated, not random. It's a system responding to what it interprets as significant. Here's the key point. This chemical cascade does not last very long on its own. If you could somehow isolate this process, if you could trigger it once and prevent any further mental involvement, you would observe something like a wave. It rises, peaks, and then falls back to baseline. The duration of that wave is typically on the order of about 60 to 90 seconds. Think of it like lighting a match. You strike it, it flares up, burns brightly for a short time, and then goes out. The match does not burn forever. Its energy is limited. The system returns to equilibrium. Your body behaves in a similar way. It is constantly trying to maintain balance. What scientists call homeostasis. Any disturbance creates a response, but that response is designed to be temporary. This is not a theory in the abstract sense. It's grounded in measurements. We can track hormone levels in the blood. We can measure heart rate variability. We can observe how long it takes for certain chemicals to be broken down or reabsorbed. And again, we see the same pattern. A surge, followed by a decay. So when we talk about a 90-second moment, we are not talking about a feeling in the poetic sense. We are talking about a physical event, a measurable change in the state of your body that unfolds over time. What makes this idea so surprising is not the biology itself. The biology is fairly straightforward. What's surprising is the implication. If the body's initial response is so brief, then why do our experiences feel so long-lasting? That question doesn't belong to this first layer of explanation. For now, we stay with what we can observe clearly. A trigger occurs, a signal spreads, chemistry changes, the system returns to baseline, a complete cycle. And under normal conditions, that cycle is short. Now consider a simple mental experiment. You're walking through a quiet room, and without warning, there's a sudden, sharp sound. A book slams shut behind you. Instantly, your body reacts. Your shoulders rise, your heart rate jumps, your attention snaps toward the source. This happens before you've had time to form a clear thought about it. The response is fast, automatic, and physical. If we could freeze time right there and observe what just happened, we would see a cascade of events. Neurons firing rapidly, signals traveling along pathways, chemicals beginning to circulate. Your body has shifted into a different state, one that is more alert, more prepared. Now imagine something unusual. Imagine that right after that sound, your mind goes completely quiet. No interpretation, no labeling. No what was that? No memory being pulled in, no anticipation of what might happen next. Just the raw sensory event, followed by silence. What would happen? Your body would still go through its response. The chemical wave would rise. Heart rate elevated, muscles slightly tense, attention focused. But then, without any additional input, the system would begin to settle. The chemicals would be broken down or reabsorbed. Your breathing would slow. Your muscles would relax. Within roughly a minute or so, the entire event would fade, leaving almost no trace behind. It would be like a ripple on water that disappears when nothing disturbs the surface again. But that's not how things usually unfold. In reality, the moment after the sound, something else happens. Your mind begins to engage. It asks questions, often automatically. What was that? Is something wrong? Did I forget something? Even if the answers come quickly, oh, it was just a book. The process has already begun. And here's the critical detail. Each of those thoughts is not just abstract. Each one corresponds to physical activity in the brain. New neural patterns are formed, new signals are sent, and in some cases, new chemical responses are triggered. So instead of one wave, you now have multiple. The first wave came from the sound itself. The second wave comes from your interpretation of the sound. A third might come from a memory it reminds you of. A fourth from imagining what could have happened. Each one overlaps with the others, blending into what feels like a continuous experience. From the inside, it doesn't feel like separate events. It feels like one sustained reaction. But if you could slow it down like analyzing frames in a high-speed camera, you would see distinct bursts, each with its own beginning and end. Think of dropping a pebble into a pond. You get ripples that spread outward and fade. Now imagine dropping another pebble before the first ripples disappear, then another. The surface becomes complex, overlapping patterns of motion. It looks continuous, even chaotic, but it's actually the sum of many individual disturbances. Your internal experience works in a similar way. The original event, the sound is just the first pebble. What follows depends on how many additional pebbles are introduced by your own thinking. Without them, the system quiets down naturally. With them, the activity continues, sometimes far longer than the original trigger would justify on its own. This is not a flaw in the system. It's a feature of how the brain processes information. It doesn't just react, it models, predicts, and reevaluates. But in doing so, it can extend what was originally a brief physical response into something that feels ongoing. So the thought experiment reveals something subtle but important. The duration of your experience is not determined solely by the initial event. It is shaped, moment by moment, by what happens after, and much of that happens internally. Now shift perspective slightly and look at this through a more physical lens rather than a psychological one. In physics, when we describe a system, we try to separate what happens from what we say about what happens. The system evolves according to rules, energy flows, forces act, states change. The description is secondary. Your body, at its core, is a physical system. It follows rules. Signals come in, they propagate, they dissipate. There's nothing mysterious about that part. It's measurable, predictable within limits, and constrained by biology and chemistry. If a stimulus occurs, your nervous system processes it. Energy is transferred, chemical gradients shift, and then importantly, the system relaxes back toward equilibrium. This is what physical systems tend to do unless energy keeps being added. Now here's where things begin to diverge from a purely physical description. Humans don't just register events, they interpret them. And interpretation is not passive labeling. It is an active process that changes the state of the system itself. When you think about an event, replay it, analyze it, imagine variations, you are not stepping outside the system to observe it. You are injecting new activity into it. New neural circuits fire. New chemical signals are released. From a physical standpoint, you are adding energy back into the system. This creates a loop. An external event triggers a response. That response fades. But then a thought about the event arises. That thought triggers a new response. And the cycle continues. If you look at it carefully, there's no fundamental difference at the level of the body between reacting to something that just happened and reacting to something you are remembering or imagining. In both cases, neurons fire. Chemicals are released. The body shifts state. This is where the confusion begins. From the inside, it feels like a single, continuous experience. You might say, I've been stressed for hours, or I've been anxious all day. But from a systems perspective, what may actually be happening is a sequence of short-lived physical responses, each one triggered by a chain of thoughts. The distinction is subtle but important. In physics, if you observe a system that appears to be in a constant, excited state, you would ask, is there a continuous input of energy? Because without it, the system would naturally settle. The same logic applies here. If the body's baseline tendency is to return to equilibrium, then a prolonged state of activation suggests that something is repeatedly reactivating it. That something is often internal. Now, this doesn't mean the experience is unreal. The physical changes are real. The elevated heart rate, the muscle tension, the hormonal shifts, they are all measurable, but their persistence may not come from a single sustained cause. Instead, it may come from many small causes occurring in rapid succession. Another way to think about it is in terms of resonance. In physics, if you apply force to a system at just the right frequency, you can keep it oscillating. Each push arrives before the previous motion has died out, reinforcing it. The system appears to sustain motion continuously, but is actually being driven by repeated inputs. Your thoughts can act like those inputs. Each time you revisit an idea, each time you simulate a scenario, you are effectively pushing the system again. The original response hasn't fully faded, and now it's being reinforced. This is not something we are trained to notice. Our subjective experience blends these events together. We don't perceive discrete bursts, we perceive a continuous state, and that blending is useful in many contexts. It allows for coherent narratives, stable identities, and long-term planning. But it also makes it difficult to distinguish between what is being sustained externally and what is being regenerated internally. So when we say there is a difference between the initial 90-second response and what follows, we are really pointing to a difference between two kinds of processes. One is a direct reaction to a stimulus, governed by relatively fixed biological dynamics. The other is a recursive process, where the system feeds back into itself, extending and reshaping the original response. Understanding that difference doesn't require belief or interpretation. It follows from observing how physical systems behave, and recognizing that the brain, despite its complexity, is still one of those systems. Now, consider why this is so difficult to notice from the inside. The problem is not that the process is hidden. The signals are there, heart rate changes, tension in the body, shifts in breathing. The difficulty is that the mind does not experience these events as separate pieces. It compresses them into a single, continuous stream. To see why, imagine being in a large, empty room with smooth walls. You clap once. The sound doesn't just stop, it reflects. It bounces off the walls and returns to you again and again, each time slightly weaker. If the room is shaped in a certain way, those reflections can overlap, reinforcing or interfering with one another. After a moment, it becomes hard to tell which sound was the original clap and which ones are echoes. Now imagine you've never experienced silence in that room. You've only ever heard the overlapping echoes. It would be reasonable to conclude that the room itself is producing a continuous sound, but that conclusion would be slightly off. The room is not generating sound, it is sustaining and reshaping what was already introduced. Your mind behaves in a similar way. An initial event, something you see, hear, or think, acts like the first clap. It creates a pattern of activity. That pattern does not vanish instantly, it leaves traces. Neural circuits remain active for a short time. Chemical signals linger before they are cleared. During that window, the system is sensitive. It can be influenced by what comes next. Then another thought appears. It might be related to the first event, or only loosely connected. But because the system is already active, the new thought interacts with the existing pattern. It reinforces some parts, alters others, and extends the overall activity. From a distance, this looks like a continuous state. But if you could isolate each contribution, you would find a sequence. Initial signal, reflection, reinforcement, decay, repeated many times. The reason this becomes confusing is that the brain is designed to integrate information over time. It does not present you with raw, disjointed events. It constructs a coherent experience. That coherence is useful. It allows you to understand cause and effect, to build narratives, to make decisions. But it also means that the boundaries between events are blurred. Consider another analogy. Think about a long exposure photograph taken at night. Cars move through a city, and their headlights become continuous streaks of light. The image suggests uninterrupted motion, a smooth flow. But in reality, each car occupies a specific position at a specific time. The continuity is an artifact of how the information is captured and combined. Your perception works in a comparable way. Individual physiological responses, each lasting perhaps around 90 seconds or less, are combined into what feels like a steady emotional condition. You don't see the gaps. You don't notice when one response ends and another begins. The transitions are too fast, too seamless. There's another layer to this. Mirror does not store events as isolated fragments. It links them. When a new thought arises, it often activates related memories, which in turn activate other associations. This creates chains of activity. Each link in the chain can trigger its own physical response, even if the original trigger is long gone. So what you experience as a single, extended feeling may actually be a network of interconnected events, each one briefly activating the body, each one fading, but replaced quickly by another. This makes it very hard to answer a simple question. What am I reacting to right now? The answer is often not just one thing. It may be a mixture of the present moment, recent memories, imagined futures, and interpretations, all interacting within the same system. Because of this, the mind tends to attribute the entire state to a single cause. It says, I feel this way because of that. But the actual mechanism is more distributed. Multiple small inputs, layered over time, create the overall effect. From a scientific standpoint, this is not surprising. Complex systems often behave this way. They integrate inputs, smooth out fluctuations, and produce stable patterns from unstable components. But from a subjective standpoint, it creates an illusion. The illusion that the state is continuous, self-sustaining, and tied to a single source. In reality, it may be neither continuous nor singular. It may be a rapidly updated construction, assembled from many short-lived pieces that are constantly being refreshed and replaced. Now look more closely at what is actually changing inside the body during one of these short-lived responses. It's easy to speak about feeling something as if it were a single, unified event. But physically, it's a coordinated shift across multiple systems, each operating on slightly different timescales. Start with chemistry. When a trigger is detected, certain signaling molecules are released. Some act locally between neurons. These are neurotransmitters. Others enter the bloodstream and travel more widely. These are hormones. Substances like adrenaline and cortisol are often involved in responses associated with alertness or stress. These molecules don't stay in the system indefinitely. They are broken down by enzymes, reabsorbed into cells, or filtered out over time. Each has a characteristic lifetime. Some act and disappear quickly, others persist a bit longer. But none of them are designed to remain elevated forever under normal conditions. This is where the idea of a limited duration response comes from. The chemistry has a built-in decay process. Now consider the cardiovascular system. As these signals spread, your heart rate may increase. Blood vessels can constrict in some areas and dilate in others. Blood is redirected toward muscles or critical organs, depending on the nature of the response. This happens automatically, without conscious control. But again, this is not meant to be permanent. Once the signaling molecules decrease, the system begins to return to its baseline state. The heart slows, vessels adjust, circulation stabilizes, breathing also changes. You might take quicker, shallower breaths, or sometimes deeper ones. Oxygen intake and carbon dioxide release shift slightly, which in turn affects the chemistry of the blood. This feeds back into how you feel, subtly influencing sensations of tension, urgency, or calm. Muscles are another part of the picture. They can become primed for action, increasing in tension even if you remain still. This is preparation without movement, a kind of readiness. If no action follows, that tension gradually releases. But while it's present, it contributes to the overall sensation you interpret as an emotional state. Attention changes as well. Your brain does not process all information equally. During a response, it prioritizes certain signals over others. You may become more focused on a specific detail, less aware of the broader environment. This narrowing or sharpening of attention is part of the same coordinated shift. All of these processes are linked, but they are not identical. They rise and fall at slightly different rates. One may peak quickly and fade, while another lingers a bit longer. Together, they create a composite effect, a pattern that you experience as a single feeling. Now here's an important point. Even though this pattern feels unified, it does not require continuous input to end. The systems involved are self-regulating. Once activated, they tend to move back toward equilibrium unless something interferes. This is a general property of biological systems. They are not designed to remain in extreme states indefinitely. There are feedback mechanisms, both chemical and neural, that push them back toward balance. So within that approximate 60-90 second window, what you are observing is the natural life cycle of a response. Activation, peak, decay, recovery. If you could measure all relevant variables in real time, hormone levels, heart rate, neural activity, you would not see a flat line of sustained intensity. You would see curves rising and falling, overlapping but distinct. The challenge is that your subjective experience does not display these curves. It compresses them into something that feels steady and continuous. This compression hides the transient nature of each component. It makes it seem as though the state is fixed, when in fact it is constantly evolving. There's also variability. Not every response is identical. The exact duration and intensity depend on many factors. Your baseline physiology, prior experiences, the nature of the trigger, and even random fluctuations in the system. So 90 seconds is not a precise universal constant. It's more like an average time scale, a rough measure of how long the core chemical and physiological processes tend to last before subsiding. What matters is not the exact number, but the pattern. A response begins, it changes the state of the body. And then, left on its own, it fades. Understanding this at a physical level shifts the focus away from abstract labels and toward measurable processes. It grounds the experience in something observable, a temporary reconfiguration of a complex system rather than a permanent condition. Now consider the boundary between what we can measure and what we actually experience. Up to this point, the description has been fairly clean. Signals travel. Chemicals are released. Systems activate and return to baseline. These are things we can observe with instruments. We can attach sensors, draw graphs, and describe patterns with reasonable precision. But there is a gap. The gap is between those measurements and the felt experience of being inside the system. For example, we can detect changes in heart rate down to fractions of a second. We can measure hormone concentrations in the blood. We can even observe patterns of brain activity using imaging techniques. But none of these measurements directly tell us what it feels like to undergo those changes. There is no instrument that reads out anxiety or fear in the way a thermometer reads temperature. Instead, we infer those states by combining physical data with self-reports, what a person says they are experiencing. This introduces uncertainty. Two people might show similar physiological patterns, elevated heart rate, increased muscle tension, certain neural activity, and yet describe their experiences differently. One might say, "I feel alert." Another might say, "I feel anxious." The underlying physical processes overlap, but the interpretation differs. So when we talk about a 90-second response, we are describing something that is physically grounded, but not fully captured by subjective language. There is also the question of thresholds. At what point does a small change in chemistry become a noticeable feeling? There is no sharp boundary. The system is continuous, but perception is selective. Many processes are happening below the level of awareness, never entering conscious experience at all. This makes it difficult to map one domain onto the other. We can say that certain chemicals rise and fall within a certain time window. We can say that the body tends to return to baseline. But connecting that directly to the richness of human experience, thoughts, emotions, narratives is not straightforward. Another layer of uncertainty comes from feedback. The brain is not just passively receiving signals from the body. It is also predicting, interpreting, and modulating those signals. There are top-down influences, expectations, memories, learned associations that shape how incoming information is processed, so the relationship is not one-directional. It's not simply trigger body response experience. It's more like a loop. Body signals influence brain activity influences perception. Perception influences further brain activity, and that in turn can influence the body again. This recursive structure makes it hard to isolate cause and effect. If you measure a spike in heart rate, is it caused by an external event? By a thought? By anticipation of something that hasn't happened yet? Often, it's a combination. And even if you identify the physical cause, you still face another question. Why does that particular pattern of activity feel the way it does? This is sometimes referred to as the hard problem of experience, the question of how physical processes give rise to subjective awareness. It remains unresolved. We can describe correlations. We can say that certain patterns of neural activity are associated with certain reported experiences, but we do not yet have a complete explanation for why those patterns should feel like anything at all. This is where the limits of current knowledge become clear. We understand the mechanics of signal transmission fairly well. We understand the chemistry involved. We can model parts of the system with increasing accuracy, but the translation from mechanism to experience, from objective measurement to subjective reality, is still not fully understood. So when we discuss something like a short-lived physiological response, we are standing at the intersection of two domains. One is the external, measurable world of biology and physics. The other is the internal, lived world of perception and feeling. They are clearly related, but not perfectly aligned. And that misalignment is part of why this topic is so difficult to grasp intuitively. We are trying to use one kind of language to describe something that exists partly in another domain. From the outside, it looks like a set of transient physical events. From the inside, it can feel like a continuous, meaningful experience. Both descriptions are valid within their own frameworks, but the connection between them is still, in many ways, an open question. Now consider something even more subtle, the sense that your experience is continuous. At any given moment, it feels like there is an unbroken stream, one ongoing state that carries through time. If you feel tense, it seems like that tension is simply there, persisting from one second to the next. But this impression of continuity may not reflect how the underlying system actually works. From a physical perspective, the body is never static. It is constantly updating. Signals rise and fall, chemicals are released and cleared, neural patterns form and dissolve. These changes happen on very short time scales. Fractions of a second to a few seconds, sometimes extending into longer cycles, like the roughly 60-90 second responses we've been discussing. If you could observe all of this in fine detail, you would not see a smooth, unchanging state. You would see fluctuations, peaks and dips, activations and recoveries layered on top of one another. So where does the feeling of continuity come from? One way to approach this is to think about how the brain handles information over time. It does not present raw data moment by moment. Instead, it integrates information across short windows, smoothing out variations. This is useful. If perception were too fragmented, it would be difficult to function. You wouldn't experience stable objects, consistent sounds, or coherent motion. Consider vision. What you see feels continuous, but your visual system is sampling and processing information in discrete intervals. The brain fills in gaps, predicts what should be there, and constructs a stable image of the world. The result is a seamless experience. Even though the underlying data is not perfectly continuous, a similar process may be happening with internal states. Short-lived physiological events, each with a beginning, middle, and end, are combined into a single, ongoing experience. The transitions between them are smoothed over. You don't notice when one response fades and another begins, especially if they overlap in time. This creates the impression of a steady condition. Another way to see this is through the idea of temporal resolution. Any measuring system has limits to how finely it can distinguish events in time. If two events occur very close together, they may be perceived as one. In physics, this shows up in instruments that cannot resolve extremely rapid changes. In perception, something similar happens. Your awareness has a certain temporal grain. Events that occur within that window are blended together. So if your body generates a series of responses, each lasting perhaps tens of seconds, overlapping and interacting, they may fall within a range that your perception integrates into a continuous whole. Mirror also plays a role. You don't just experience the present moment, you retain traces of the recent past. These traces are not perfect recordings, but they influence how the current moment is interpreted. If a similar pattern of activity repeats, memory links them together, reinforcing the sense that it is the same feeling continuing, rather than a sequence of related but separate events. There is also prediction. The brain is constantly anticipating what will happen next. If the system has been in a certain state, it tends to expect that state to persist. That expectation shapes perception, making continuity more likely to be perceived even when the underlying signals are changing. All of this contributes to a kind of constructed stability. It's not that the body is in one fixed state. It's that the brain presents it as if it were. This has an interesting consequence. When you say, "I've been feeling this way for a long time," that statement may be accurate at the level of experience, but less precise at the level of mechanism. What may be happening instead is a sequence of similar responses, each one triggered, sustained briefly, and then replaced by another. Because they are similar and closely spaced in time, they merge into a single narrative. This is not an error in the system. It's a trade-off. The brain prioritizes coherence over precision. It gives you a stable sense of what is happening, even if that stability comes from blending many small changes into one. From a practical standpoint, this is efficient. It reduces complexity. It allows for faster decisions and clearer interpretations, but from an analytical standpoint, it hides the underlying structure. It turns a series of discrete, transient events into what feels like a continuous state, and once that transformation happens, it becomes very difficult to see the original pieces that make it up. Now consider a different question. If these responses are short-lived and self-limiting, why do they seem to restart so easily? The body, as we've seen, has a tendency to return to equilibrium. Chemical signals decay, heart rate stabilizes, muscles relax. Left alone, the system quiets itself. But in real experience, the system is rarely left alone. Something keeps reintroducing activity. One way to understand this is to think of the brain not as a passive receiver, but as an active generator of scenarios. It is constantly constructing models of the world. What is happening, what might happen next, and what it all means. This modeling process is continuous. Even in the absence of strong external input, the brain generates internal activity. Memories, predictions, imagined situations. These are not abstract in the sense of being detached from the body. They correspond to real patterns of neural firing, which can influence the same physiological systems involved in direct reactions. So a thought is not just in your head in a vague sense. It is a physical event that can trigger further physical changes. Now imagine that a particular pattern, say, a certain memory or concern, becomes active. It produces a mild physiological shift. That shift feeds back into the brain as a signal. Something is happening. The brain then tries to interpret it, often by referring to the same pattern that generated it in the first place. This creates a loop. The thought influences the body. The body influences perception. Perception reinforces the thought. Each cycle may be brief, but if they occur in rapid succession, the system can appear to stay in a sustained state. Another way to look at this is through timing. Recall that individual responses have a certain duration, tens of seconds, perhaps around a minute or so. If a new triggering thought arises before the previous response has fully decayed, the two overlap. The second response begins while the first is still fading. If this continues, if new triggers keep arriving at intervals shorter than the decay time, the system never fully returns to baseline. It remains in a partially activated state. This is similar to how repeated inputs can maintain motion in a physical system. Imagine pushing a swing. One push sets it in motion, but the swing will eventually slow down due to friction and air resistance. However, if you push it again before it stops, and continue doing so at the right intervals, the motion is sustained. The swing appears to keep moving continuously, but in reality, it is being driven by repeated, well-timed inputs. The body can behave in a comparable way. Each thought or interpretation acts like a small push. On its own, it produces a limited response, but when repeated, it can maintain a larger pattern of activity. There is also the role of relevance. The brain does not treat all thoughts equally. It prioritizes those that seem important, especially those related to uncertainty, potential threats, or unresolved situations. These are more likely to be revisited, reconsidered, and simulated again. Each revisit is another input into the system. From the inside, this does not feel like restarting a process. It feels like continuing one. The distinction between new and ongoing becomes blurred because the content is similar and the transitions are smooth. But from a mechanistic standpoint, there may be multiple initiation points, many small beginnings, rather than one long, uninterrupted event. There's also an efficiency aspect. The brain is designed to conserve information that might be useful. If something seems unresolved, it keeps it active in some form, ready to be processed again. This increases the likelihood of repeated activation of the same neural circuits and therefore repeated physiological responses. So the system is not only reactive, it is also self-sustaining under certain conditions. This doesn't mean it is locked in place. The underlying processes are still transient. Each individual response still has a rise and fall, but the sequence of responses can create a pattern that appears stable over longer periods. What makes this particularly difficult to notice is that the triggers are often subtle. They may not be clear, distinct thoughts. They can be fragments, images, associations, partial memories, or even bodily sensations that the brain interprets and feeds back into the loop. Because these triggers are internal and often below conscious awareness, it can seem as though the state is simply there, without a cause. But when viewed as a system, it becomes more like a chain of events, each one small, each one temporary, but together forming something that looks continuous. And that continuity, again, is constructed from repetition, timing, and the brain's tendency to keep certain patterns active. Now take a step further and strip away the everyday language entirely. Forget words like emotion, feeling, or even thought for a moment. Treat the body as a physical system, no different in principle from a complex arrangement of interacting particles and fields. In that description, everything reduces to motion and interaction. Neurons are cells, but at a deeper level, they are structures where charged particles move. Electrical signals are not abstract. They are flows of ions across membranes, driven by differences in potential. Chemical messengers are molecules binding to receptors, changing configurations, triggering cascades of reactions. At this level, a thought is not a separate category of thing. It is a pattern of activity. Specific pathways activated, specific signals exchanged, specific configurations temporarily formed. Now consider what happens during one of these short-lived responses. A particular pattern is initiated. Charges move, molecules are released, connections between neurons become more or less active. This pattern spreads through parts of the system, influencing other components. Then, because the system is not being continuously driven, the pattern begins to decay. Signals weaken, chemicals are cleared, activity subsides. This is not fundamentally different from other physical processes. If you disturb a system, heat a metal, displace a pendulum, compress a spring, it responds according to its structure and then relaxes when the driving force is removed. The body behaves similarly, though with far greater complexity. Now here is the crucial point. If the same pattern is initiated again, the system does not remember it in the sense of replaying a recording. Instead, it reconstructs it. The same or similar neural pathways activate. The same kinds of signals are sent. The resulting physical state resembles the previous one, sometimes closely enough that it feels identical from the inside. But each instance is a new event. Even if two patterns are nearly identical, they occur at different times, under slightly different conditions. There are always small variations, none in the system, differences in timing, fluctuations in chemical concentrations. From a strict physical standpoint, no two moments are exactly the same. Yet the brain groups these similar patterns together. It treats them as instances of the same state. This is an act of categorization. Instead of seeing each configuration as unique, the system identifies common features and labels them as belonging to a single category. That category might correspond to what you call a particular feeling or mood. So when you say this is the same feeling, what may actually be happening is that multiple distinct physical events are being grouped under one label because they share enough similarities. This grouping is useful. Without it, experience would be fragmented beyond recognition. You would not be able to generalize, to learn, or to anticipate, but it also hides the underlying discontinuity. Each response begins. Each response evolves. Each response ends. And then another begins. If these events occur in rapid succession, with overlapping timing and similar structure, they create the appearance of persistence. From the outside, it might look like a sustained state. From the inside, it feels like one continuous experience. But from the perspective of the underlying mechanics, it is closer to a sequence of recreations. Another way to see this is to think about stability. In many physical systems, what appears stable is actually dynamic. A flame, for example, seems constant, but it is a continuous process of fuel consumption, chemical reaction, and heat transfer. The shape persists, but the newt, the actual particles involved, are constantly changing. Your internal states may have a similar character. They appear stable, but they are maintained through ongoing activity. Not a single unchanging condition, but a process that keeps regenerating a familiar pattern. This leads to an important implication. If the pattern is not being actively regenerated, if the specific neural activity does not recur, the state does not persist on its own. It fades, just like any other physical process that is no longer being driven. So what feels like something solid and enduring may actually depend on continuous reconstruction at the microscopic level. And that reconstruction is happening whether you are aware of it or not. Seen this way, the 90-second moment is not a special case. It is simply one timescale within a broader system of constant formation and dissolution. A system in which what appears continuous is built from events that are in themselves temporary.